may have heard about power factor correction, or PFC. Today I am sharing a very simple overview of PFC. So what is power factor correction, or PFC for short? If the load is purely resistive, voltage and current are in phase. If the load is inductive, the voltage will lag the current by a 90-degree phase angle. When you have a capacitive load, the voltage leads the current by a 90-degree phase angle. Almost any power stage is going to have a combination of capacitance and inductance, which will introduce a phase angle between the voltage and current. The phase shift creates what is called the power factor triangle between active, reactive, and apparent power. So what is the power triangle? The power triangle describes the complete picture for AC power. The apparent power is what you think you are getting. The active power is what you are actually getting. The reactive power is not used, but it does get returned to the power grid at a loss. A popular analogy is to think of this in terms of a pint of beer. This is the apparent power. This is the active power. And finally, the foam represents the reactive power. So the job of the PFC is to simply put the voltage and current back into phase. Ideally, the PFC is 1, which means there is no longer a phase angle between the voltage and the current. Does having a PFC of 1 improve efficiency? Well, not for the local power supply. While the PFC itself can be very efficient, there is still a net power loss. So why then do we care about PFC? Having perfect power factor correction actually reduces stress on the power grid. So how does PFC help to improve the grid? Your power company has to send you enough apparent power to support the active power you actually require. So what is going on here? For example, if your computer's power supply has a power factor of 0.5 and requires 100 watts of power, your power company will be sending 200 watts of power. The computer will use its 100 watts and the remaining is returned back to the source, but at a loss. This is due to I²R losses in the power lines. Another thing to consider with power factor correction is total harmonic distortion, or THD. THD is a measurement of how much the ideal sinusoidal current and voltage waveforms have been distorted. The resulting noise is injected back into the grid and can have an impact on other electronic devices connected to the same grid. So what is THD actually? THD occurs due to a superposition of signal harmonics. For example, if the frequency of this signal is 100 Hz, the first harmonic would be at 200 Hz. The harmonics ride on the fundamental causing the distortion. Note there are many higher-order harmonics which cause further distortion. There are several standards, each tuned to specific applications or regions as to what THD requirements need to be met, some examples of which are IEEE 519, EN 50160, and IEC 61000-3-2. When discussing PFC, there are 3 conduction modes to be aware of. This helps to better pick the right controller for a given application or power level. In discontinuous conduction mode, or DCM, the inductor current goes to 0 every switching cycle. In transition or critical conduction mode, the inductor current just gets to 0 before the next switching cycle. And finally, there is continuous conduction mode, or CCM, where the inductor current never goes to 0. So what is the difference between these different modes of operation? Knowing which controller to choose comes down to knowing the pros and cons of each approach. A DCM PFC has 0 current switching and is a fixed frequency topology. The biggest pro to this type of PFC is that it will have the best light load efficiency. The downside is that it has the worst over THD and overall efficiency. The transition mode controller also has 0 current switching, and the operating frequency will vary as a function of the load. This also is very good with light load efficiency, and the overall efficiency is higher than DCM. The downside to the transition mode controller is that the peak currents are high, which can limit the power range. Also, the THD is not as optimal as CCM. A CCM controller is also a fixed frequency topology. With CCM, you will have the lowest THD and the best efficiency at full load. This also uses a smaller inductor for the same power level as the other modes of operation. The con of the CCM PFC is that the rectification diode tends to be more expensive as it has to have a very fast recovery time. Also, since inductor current is always flowing, its light load efficiency is compromised. The CCM operation can also be a little more difficult to design and optimize. I hope you found this informative. To see more, please like and subscribe